Hello students, this is our lecture 9. We are discussing the normal distribution. The content of our today's lecture is we will learn normal approximation to binomial distribution, then normal approximation to Poisson distribution, then central limit theorem, and we will solve some examples and problems based on the normal distribution. So let's start the session. First topic of our today's lecture content is normal approximation. Normal approximation to Poisson distribution. First of all, we will discuss for Poisson distribution. Then we will discuss for binomial. Concept is statement is if x follows Poisson distribution with parameter m, then the probability distribution of x minus m divided by under root of m tends to normal 0, 1 as m tends to, let's see its proof. Let x follows Poisson distribution parameter m. Its mean is m and variance is also. The MGF of Poisson distribution is e raised to lambda here it is m into e raised to t minus. Now we have to find out the probability distribution of this x minus m upon root m. So we will solve this by using MGF approach. So we will solve, or we will obtain the MGF of this x minus m upon. Consider MGF of, we call this as z, x minus m is equals to, we write this as MGF of 1 upon root m x minus m upon root m, that is root m of. So this will be solved by the properties of MGF. We know the property of MGF, that MGF of x plus a, change of origin property, is equals to e raised to at x of t, and MGF of ax of t is mx of at. So these two property we will use here. So this is the origin part minus root m. It will be e raised to a. A is minus root m t into mx of at. So a is 1 upon root m, is 1 upon root m t. So t upon. Now just plug the value of this t upon root m in the MGF of Poisson distribution. So solve this. E raised to minus mj of Poisson distribution is e raised to lambda, that is e raised to m into e raised to, instead of t, replace this by t by root m minus 1. This is the mz of t. Now take log on both sides. Take log. This is minus m into t plus m into e raised to t upon root m minus all this minus root m plus m into. Now use the concept of e raised to x, that is 1 plus, we know the series e raised to x is equals to 1 plus x square upon 2 factorial plus x cube upon factorial plus and so on. So use this series here. 1 plus x is t upon root m plus x square, that is t square m upon 2 factorial is factorial plus t cube upon this raised to 3 by 2 factorial and so on. Hold this term and at last this is minus 1. शेवटी या ठिकाणी minus 1. So this 1 minus 1 get cancelled. If you multiply this m inside, you will get minus root m t plus this m upon root m is root m into t plus this mm get cancelled. This is t square upon 2 plus this is t cube upon this is m and this is m raised to 3 by 2. So here it is m raised to 1 by 2, and the next terms are the next term where the order of this m is greater than this 1 by 2 or greater than 1. That's it. Plus so on. So this is log of mz of t. So now here the next terms are where the denominator powers of this m are larger than 1. Okay. So if you take the limit as m tends to infinity, log of mz of t, so this get cancelled. This is t square upon 2, and all these terms, limits of all these terms will be 0. And now if you now exponential on both sides, so limit m tends to infinity, mz of t is equals to e square e raised to t square upon. So this is nothing but which is the mgf of, which is mgf of normal 0 comma. Okay, and therefore by uniqueness property of mgf, uniqueness property of mgf, the probability distribution of x minus m upon root m follows normal distribution. Okay. Similarly, we can prove for binomial distribution also. The next is normal approximation. Normal approximation to binomial distribution. On the same lines, we will prove this result also. Statement. Let X follows binomial distribution with parameter n comma p. Then probability distribution of x minus the mean np divided by under root of variance npq. This tends to normal 0 comma 1 as n tends to infinity and for the smaller values of. Let's see its proof. We will prove very similar as of earlier. So let x follows binomial comma p. Its mean is np, variance is npq. Its mx of t is q plus p into e raised to t raised to n. Consider mz of t, which is equals to x minus np on under root npq of t, which is equals to, by change of origin and scale property, this is e raised to, let's write this in one more step, mgf of 1 upon under root npq x, this is coefficient a, minus np upon under root npq. So this is change of origin, np upon root npq. This is max, change of scale. Will be e raised to minus np e raised to at mx of this is 80. It is 1 upon under root npq, mx of 80 into t. This is t upon under root of np. Okay. So now mgf of binomial is q plus p times e raised to t raised to n. So instead of t, replace t upon under root npq in the mgf of binomial distribution. So this is q plus p to e raised to, instead of t, replace this by t upon npq raised to n. This is the mz of t. Now take log on both sides. So we will get this minus np under root of npq plus n times log of q plus p into e raised to t under root of npq. This is the log of mz of t. Now solve this. Plus n times log of q means 1 minus p so this will be minus p upon under root of npq plus n times log of log of 1 plus if you take p constant outside, this is e raised to t upon under root of npq minus 1. So this is your log of mz of t. Now this will be, so this is a, and we will use the series log of 1 plus a, which is equals to a minus a square by 2 plus a cube by 3 minus a raised to 4 by 4 and so on. So this will be log of mz of t. This is equals to minus np divided by under root of npq t plus n times log of 1 plus a. This is a. So it is a is p into e raised to root of this npq minus 1. This is a minus a square. This is p square into e raised to p square upon npq minus 1 bracket square and so on. Actually, there is no need of all these next terms. Why so? Because if we solve these terms, we will get the higher powers. Let's see how. Log of mz of t equals to minus np divided by, this is pq, plus, now we will use the series e raised to x. This is n into series of e raised to x is 1 plus x, that is t upon under root npq. This is 1 plus x plus x square, that is t square into 2 factorial plus t cube npq raised to 3 by 2 into 3 factorial. Okay. So if we solve only this bracket, we will get the higher powers of these denominator terms. What we are doing in the next terms, पुढच्या टर्म्स मध्ये आपण काय करणार आहे तर लिमिट्स घेणार आहेत ॲज इट इज टू इन्फिनिटी, आणि यांच्या ज्या टर्म्स आहेत तर या इथूनच त्या हायर पॉवर्सला जात आहेत. या पुढच्या जर टर्म आपण या ठिकाणी सॉल्व्ह केल्यात तर सर्व टर्म या डिनॉमिनेटरला 1 अपॉन n रेस टू समथिंग या हायर टर्म्स जाणार आहेत. म्हणून या पुढच्या टर्म्स आपण वी आर नॉट सॉल्विंग दोज टर्म्स बिकॉज इफ यू टेक द लिमिट ॲज इट इज टू इन्फिनिटी, लिमिट ऑफ ऑल दीज नेक्स्ट टर्म्स विल बी 0. ठीक आहे. ही टर्म आणखीन एकदा एक्सप्लिसिटली सॉल्व्ह करून घेऊयात. This is e raised to x minus 1. This one and this one will be cancelled. So now it is npt 1 under root of npq. These both terms will be cancelled. Next will be, this is np get cancelled. This is t square upon 2q, like this. So this is the log of mz of t, and if you take limit m tends to infinity, log of mz of t. आता या इथं पुढच्या टर्म्स ज्या आहेत या पुढच्या टर्म्स मध्ये दिस इज टी क्यूब अपॉन n raised to 1 by 2 q raised to 3 by 2 3 factorial अशा टर्म्स आहेत. पुढच्या सर्व टर्म्स मध्ये डिनॉमिनेटरला 1 अपॉन n raised to समथिंग आहे, आणि त्याचं जर लिमिट आपण घेतलं तर ते सगळं 0 होईल आणि शिल्लक फक्त राहील t square upon 2q. and if for p is very small, so this limit will be हे जर सॉल्व केला आपण, it's simply only t square upon for small and if you take the exponential now, limit m tends to infinity, log of mz of t na. So if you take the exponential mz of t, it is equals to e raised to t square upon, which is the mgf of, which is mgf of normal 0 comma, therefore by uniqueness property of mgf, z which is equal to x minus np upon under root of np cube. This follows normal 0 1 if x is binomial np, as n tends to z. Next concept is central limit theorem. Next concept is central limit. Its statement is, if we have xi, this is the sequence of IID random variables, IID random variables with expectation of xi mu, and variance of xi is equals to sigma square. Then summation, if we have the sequence Sn, which is equals to summation of xi, सर येण्यापेक्षा दोघं फॉर्म मध्ये आपण लिहूयात. देन समेशन xi, or then we may call x bar follows normal distribution as large n, or x bar minus expectation of x bar divided by under root of variance of x bar is equals to x bar minus mu on sigma upon root n. This follows normal 0, 1 distribution. ठीक आहे. xi हे कुठलंही डिस्ट्रीब्युशन असू द्या, आयदर डिस्क्रीट ऑर कंटिन्युअस, याचा तुम्हाला मीन माहिती असेल, व्हेरियन्स माहिती असेल, तर एक्स बारचं डिस्ट्रीब्युशन हे नॉर्मल 0 1 ला जातं. ठीक आहे. दिस इज द सेंट्रल लिमिट थेरम. That's it. So the theory part of this normal distribution is over. Now we will solve some examples. Till now, I think we have solved 2 or 3 examples. Let's try to solve some more problems. Example number 4. Let's solve an example based on central limit theorem. Okay. Let's take another example. Here, suppose heights of soldier follows. What is given here? Example, suppose height of soldier follows normal distribution with mean it mean 170 centimeter and variance 50 centimeter square. Question is, in regiment of 1000 soldiers, how many would you expect to be? Would you expect to be over 180 centimeter tall? Okay. So what is given here? Height of the soldier. So let's denote it by x. X is what? Height of it is given that its distribution is normal. Its mean is 170 and variance is 50. And the question is, in a regiment of 1000 soldier, how many would you expect to be over 180 centimeter tall? So to find out this, we have to find out the probability of x greater than all this. We will solve this by let's standardize this. X minus u greater than 180 minus mean is 170 divided by sigma is 50. This is equals to probability of z greater than is 10 upon root 50. So if you solve this, this is probability of z greater than 1.41. So you can easily see this value from the statistical table, and it is 0.0797. So this is the probability. If you multiply this probability by this number 1000, then the total number of soldiers out of out of 1000 having height above 180 centimeter is equals to 1000 multiplied by 0.079, so which is equals to 79.2 approx 70. So out of 1000 there are 79 soldiers are there whose height is above 180 this way. So let's solve one or two examples. Let's take x follows normal distribution 0, y follows normal distribution with parameter 0, 1. X and y are independent. And y are independent. Find probability of x plus y greater than or equals to root 2 x minus y less than or equals to 0. So here it is given that x follows normal 0 1, y follows normal 0 1, x and y independent. So since x and y are independent, x plus y follows normal distribution with mu1 plus mu2 is 0, sigma 1 square plus sigma 2 square, and x minus y follows normal mu1 minus mu2, so it is similar 0 comma. So since x and y are independent, therefore x plus y and x minus y are also independent. Since x comma y are independent, x plus y and x minus y are also. So probability of this x plus y greater than or equals to 2 comma x minus y less than or equal to 0, this is equals to probability of x plus y greater than or equals to root 2 multiplied by probability of this x minus y less than or equal to 0. So this is equals to the distribution of x plus y is normal 0 comma 2. If you standardize this, root 2 minus 0 divided by standard deviation, that is root 2, into probability of this is z less than or equal to 0 minus 0 0 upon root 2. So this probability is z greater than 1 into probability of z less than 0. So probability of z greater than 1 is 0.1586 and z less than 0 is 0.50. To solve this, we will get 0.079. This way we have to solve. And last example which is based on central limit theorem. Then we stop. If xi is x1 x2 up to x100, ID random variables with Poisson distribution with mean 4, find approximately probability of summation xi I is running from 1 to 100 greater than 430. So this example we will solve with the help of central limit theorem. What is given? Xi's are IID random variables. So Xi's follows Poisson distribution with parameter 4. So expectation of Xi is 4. Variance of Xi is also. Poisson distribution साठी mean आणि variance हे सेम असतात. सेंट्रल लिमिट थेरमचा प्रॉब्लेम सॉल्व्ह करणं म्हणजे काय, की जी काही सिक्वेन्स दिलेली असते तर ह्या सिक्वेन्ससाठी आपल्याला मीन आणि व्हेरियन्स फाइंड आउट करून घ्यायचे असतात. सो हियर लेट Sn is equals to summation xi I equals to 1 to find out the expectation of Sn is nothing but expectation of summation xi, which is nothing but summation of expectation. So which is nothing but expectation of xi is 4. Sum how many times? 100 times. It is 100 into 4 equals to 400. Similarly, variance of Sn is equals to variance of summation of xi, which is sum of variance of xi. This is equals to 100 into again 4, which is 400. So now use the central limit theorem. So probability of, consider probability of summation xi, I is running from 1 to 100 greater than 430. Now apply central limit theorem. Okay. So this is Sn greater than, just wait, uh, summation xi minus expectation of summation of xi divided by under root of variance of summation xi greater than 430. Its mean is 400 and square root of 40 is 20. So this is by central limit theorem. We apply central limit theorem. So this is z, standardize, 430 minus 400, that is 30 upon 20, which is nothing but probability of z greater than 1. So you can see this probability easily from the statistical. That's it. So this way we have to solve the examples of central limit theorem. Whatever the sequence is provided, we have to find out its mean and variance, and we have to apply the central limit theorem. That's it. So students, we have covered all the topics of theory and examples of normal distribution, and this chapter normal distribution is over here. So for this lecture we stop here. Thank you.